Today we'll be looking at exponents. Our objectives are to identify bases and exponents, to use the product rule for exponents, to use the quotient rule for exponents, to use power rules for exponents, to discuss zero exponents, discuss negative exponents, and to examine rational exponents. Now I know this sounds like a lot of material, but a lot of this will be a review for you, and I realize that. Part of it, however, may not be, and I just need to make sure that we're all on the same page before we continue on into exponential functions. So let's begin by discussing bases and exponents. When I give you something that looks like this, 3 raised to the 5th power, first of all, let me make sure you understand what that means. It means that I have 3 multiplied times itself 5 times. And just to make sure that we are all still together, this is called the base, and this is called the exponent. So the 3 is the base, and the 5 is the exponent. The base doesn't always have to be just one number. In this case, the base is 2x, and the exponent is 3. It still means the same thing. It means that I have 2x multiplied times itself 3 times. Now let's take this and go a step further with it. Let's look at the product rule. When I have a to the m times a to the n, that's equal to a to the m plus n. In English, what that says is that if you're multiplying something with like bases, meaning this and this are the same, then you can add their exponents. And here's what it looks like. If you have x to the 4th times x to the 3rd power, because these two are the same, you have the right to add those exponents, and you get x to the 7th power. It also holds true in a case like this when the base is 2x. As long as this base is the same, what you get is that base. Notice I didn't multiply anything there. I simply wrote the base and added the exponents. Let's look now at the quotient rule. If you have a to the m divided by a to the n, then that is equal to a to the m minus n this time. Here's how it looks. X to the 5th power divided by x to the 3rd power is equal to x raised to the 5 minus 3 power, which is nothing more than x squared. I do want to show you another way to remember this, because for some of you this will help. Remember that x to the 5th is just 5 x's, and that's divided by x to the 3rd power, which is just 3 x's all multiplied together. If you were to start canceling that one and that one, that one and that one, that one, and that one, what you would find is that you have 2 x's left over, just like you had right here. And so your answer is still x to the 2nd power. And I wanted you to see that just because for some of you that will help it make a little more sense. We now have 3 power rules. The first one says if you have a to the m power, and then that is raised to the n power, what you get is a to the m times n power. This is the only time you will ever multiply exponents. And here's what it looks like. If you have x to the 3rd power raised to the 6th power, then that would be equal to x to the 18th power. 3 times 6 is 18. Let's continue with another power rule. This time I have a times b raised to a power, and this rule gives me the right to break that apart into 2 pieces, both of which are raised to the m power. Here's how it looks. If you have 2x raised to the 5th power, you have the right to break that apart into 2 to the 5th power times x to the 5th power. And you might say, why would I want to do that? Well, the answer to that is because now you can simplify this part. 2 to the 5th power is nothing more than 32 times x to the 5th power. And let's go one more step here with another power rule. If you have a divided by b, all raised to the m power, you have the right to break that apart into a to the m divided by b to the m power. And here's how you can use it. If you have 2 over x raised to the 4th power, you can break it apart into 2 to the 4th power divided by x to the 4th power. And once again, you can simplify this part right here because now we're down to just where it's a number. So 2 to the 4th power is 16 divided by x to the 4th power. Let's look now at zero exponents. If I have a to the 0 power that is equal to 1 as long as a is not equal to 0. That holds true for x to the 0 power provided they tell you that x is not equal to 0, then x to the 0 power is equal to 1. What about 5 to the 0 power? Well, we know that that is always equal to 1. Let me give you one more. What about negative 3 to the 0 power? Well, that is also equal to 1, but I've got one more I want you to look at. What about this negative 3 to the 0 power? I need to remind you here, this exponent applies only to what it touches unless there's a set of parentheses that tells you otherwise, like this one did. So in this case, what I have is a negative, and then it is the 3 that is raised to the 0 power. Well, let me ask you, what is 3 to the 0 power? Well, that's just a 1. So what we actually have here is a negative 1 for a final answer. Sometimes things like that can sneak up on us if we're not careful, so I just wanted to remind you of that. And now let's look at negative exponents. A to the negative n power is equal to 1 over a to the n power. Well, what that says to us is x to the negative 2 power is equal to 1 over x squared. Now I want to focus a little bit longer on this one because you can use this in a couple of different ways, and I need you to see these. What this rule actually does is give you permission to rearrange an expression so that it is rewritten using positive exponents. Let me explain what I mean by that. If you have an expression where there are negative exponents, what we're going to do is move the variable that that exponent is attached to the denominator if it's in the numerator to start with. Likewise, if it's in the denominator to start with, we'll move it to the numerator. Let me show you how this works. If I give you this expression, I want you to look at this, and the first thing we're going to do is play a little game, and you know how exciting my games are, called Stay or Go. We're going to play Stay or Go to determine which variables should move, and let me tell you how we'll do that. We'll simply look at their exponents. Any exponent that is positive will stay right where it is. Any exponent that is negative will cause that variable to move, and the sign of the exponent will change. Let me show you what I mean. In this one right here, I would ask you, does this stay or go? Because the 3 is a positive 3, you'll tell me it stays. Then I'll ask you, does this stay or go? Because the exponent is negative, you should tell me it goes. And when I say go, if it's in the numerator, it goes to the denominator. So here's what your problem would now look like. I still want to focus on things that need to move. Well, once again, I see a negative exponent here, so I need to move that. It will move to the numerator, and its exponent will become a positive 4. I know there's some simplifying we can do, but let's keep moving things until we're all done moving, and then we'll simplify. Look at this one. Once again, I see a negative exponent. It will need to move to the numerator, and when it does, the 7 will become positive. So here's what it looks like now. X to the 3rd power, x to the 4th power, y to the 7th power, divided by y to the 5th power. Now, based on the exponent rules that we've just been looking at in this lesson, we should be able to combine these two things. They're like bases, and they're multiplied together. So when I combine those, I get x to the 7th power times y to the 7th power over y to the 5th power. Am I done? Well, once again here, I see something else that can be simplified. Y to the 7th divided by y to the 5th. Remember, you could write that out as something that looks like this and then start canceling. When you did that, you have 2 y's left over, and they're in the numerator. You could also say, I'm going to use the quotient rule here, 7 minus 5 is 2. Either way you go, your final answer is x to the 7th power times y squared. In some of your problems, they may ask you to write your answers using positive exponents. This is the step you use to make that happen. Remember, it's simply a matter of moving things with negative exponents to the denominator if they started in the numerator, and to the numerator if they started in the denominator. Our last type of exponent to look at today will be rational exponents. Instead of using the word rational there, we could use the word fractional exponents because that's exactly what we'll be looking at. This time our exponents are fractions. And I need you to understand this is nothing more than a fancy way of writing a radical. The base becomes the radicand. The denominator of your fraction becomes the index, and the numerator of your fraction becomes the power right here. Let me show you how it looks. If we have x raised to the 1/2 power, that is equal to the x comes right here, the denominator becomes the index, and the numerator becomes the exponent right here. Now let me remind you of a couple of things here. Anytime we have an exponent of 1, that's really unnecessary for us to write. All we need to do is write the x, and I also need to make sure that you understand that anytime we have a square root, that 2 is also something that is unnecessary to write. The index is understood to be a 2 unless you're told otherwise. So you could just as easily write this simply as the square root of x. Let's go one step further with this. What if I gave you 25 to the 1/2 power and asked you to simplify that? Well, by now you realize you could write that as the square root of 25, which is equal to 5. I also want to show you that you could do these same steps on your calculator. You would enter 25 raised to the 1/2 power. Please make sure that you remember to put that fraction in parentheses, and if you do, when you hit enter, your calculator will give you the same 5 that we got just a minute ago right here. I realize that part of this lesson may have just been a refresher, but there may have been a couple of things that were new to you. Just wanted to make sure we're all together before we continue into exponential equations. Let me leave you now with my thought for the day. The beginning is the most important part of the work. That holds true even for things like homework. Sometimes you just have to get started. I'll see you again soon. Bye-bye.